Okay, good morning, lads and ladies. Welcome back to College Algebra. Let me go ahead and turn this off. Sorry. Like many of us fixated on what's going on in Europe right now. Let's begin. So today is our last class meeting before exam 2. Exam 2 is next Tuesday, and we'll cover all the material that we've talked about since exam 1. So that's, proportionality, power functions, polynomials, rational functions, and radical functions. So two people actually, and I thank you guys for this very much, pointed out to me that the test 2 review quiz was actually password locked, and that's quite silly. I don't know why that was the case, but I have gotten rid of that password lock now. It is open, so you can get in there and work that at your leisure. If you do have any questions about any of the problems in the review quiz, I strongly encourage you to talk to me. Come to an office hour or send me a picture of your work. Anything that is giving you a hard time here is something that we absolutely should talk about together, because as you've seen, the test itself is quite similar to the review quiz. So the more mastery you can gain of the problems in the review quiz, the better you are likely to do on the test. So make sure you work these problems honestly, independently, and in good faith. There is no point in hacking your way through these problems. Work them until you get them, until you are 100% confident with them. My intent for us today is just to do kind of whatever you guys want to do, whatever you feel would be most helpful for you coming into the test. If you like, we can go over the activity problems that we didn't get to do last time. I think the third problem we didn't get to review together. Or if there are homework problems you would like to look at, quiz problems you would like to look at, anything at all, it is your day. So this is MAC1105, section 015, which is a college algebra class. The date today is the 24th of February, and today we are just reviewing for exam 2. And of course, the announcement that it's relevant is that exam 2 is next Tuesday. The date for that is, let's see, the 1st, 3/1. And this will be just like last time. It will be in class. And the proctoring mechanisms will be the same as they were last time. We'll be using Honor Lock and Zoom on our phones. And thankfully, it's not going to be the case. At least I certainly hope it's not going to be the case this time that I get a call from my son's daycare requiring me to come pick him up in the middle of the damn test. So that should go a little bit more smooth than it did last time. But everything else is going to be the same. So remember the things you need to do. Let's say, how do I say this? Procedures. For the test. It is exactly the same as last time, but I don't think it hurts to reiterate. You're going to sign in. Oh, not saying sign into Zoom on your phone. Go through the Honor Lock on your PC. Then navigate to the test and my open math. And I know a handful of folks had a hard time getting Honor Lock to do all the things that they needed it to do last time. The second time through, that usually goes a lot more smoothly once you've seen exactly what it is they require you to do and in exactly what order. But the system will be the same as last time. You won't lose time if Honor Lock is giving you a bunch of shit. The timer won't start until you actually get into the test. Of course, then you're going to complete the test in my open math. And you're going to write full solutions on your paper. And then once the test is done, you'll scan and upload the written work to Canvas. Now, I did notice last time a few folks took pictures of their work with like just a regular picture and then converted that into a PDF. Please don't do that, right? Please use something like Cam Scanner or Adobe Scan or Microsoft Lens or the Notes app to produce a proper scan. I know it might seem like a little difference, but it's actually a pretty big difference. If I can't read the written work, then I can't give you partial credit. I want to do that, right? I very much want to give you all the partial credit that I can, but if you just snap a photo and convert it to a PDF, it might be completely illegible. That is something that happens a lot for several reasons. Sometimes the picture is just poor quality. Sometimes the process of converting it into a PDF compresses or changes the resolution, does things that are not what we want them to do. So please scan using Cam Scanner or Adobe Scan or Microsoft Lens or the Notes app if you're on iPhone. Okay, I'm pretty sure all of those are free. If you want to use something else, that's fine, but please don't just snap a picture and convert it to a PDF because those never come out well. If I'm honest, I don't have time to like go back and forth and be like, can you give me a better quality scan, blah, blah, blah. So if you want to get partial credit on these questions, which I know everybody does, just produce for me something I can read and I will go through and make sure you get that partial credit. Okay. Questions about the test procedures? What's expected of you? Anything like that? Alrighty then. If you could, please start letting me know what you guys want to see. So today, yeah, thank you. Just like Samantha did there in the chat, let me know what problems you guys would like to see for the review. So Sam just typed question 22 and 27 on homework 12. Go ahead and hit me in the chat with all the shit you guys want to see today. Anything that you think will help you for the test. This can be homework problems, they can be quiz problems, they could be general questions about topics or examples that you want to see something similar to. Just in the chat there, type whatever it is you want to see for today, and we will do it. Go ahead and navigate over to homework 12. Yes, homework 12. '22 and 27. Sure. Yeah, I'd be happy to do that. All right. So 22 has a subtle thing in here. They tell us that a rational function has a vertical asymptote at x equals 3, a horizontal asymptote y equals 0, and a hole in the graph at the point 1, -4. And then he asked for the domain and the range. If I'm completely honest here, and this is me violating the credo of the math teacher a little bit, right? Tell the truth, tell the whole truth. Tell the truth, tell nothing but the truth, but don't tell the whole truth. The whole truth is that this question isn't quite answerable. We don't actually have enough information to say for sure what the range is. But if you think just about the things that that we can expect, then this can be answered well. So this is what I'm going to have to send off to our committee for a little bit of revising. But let's do our best. So the VA, this is number 22, 12. We've got a VA, x equals 3. I'm just going to copy this down, then we'll switch back over. We have a horizontal asymptote, y equals 0. We have a hole at 1, -4. And that's, okay, so find domain and range. So the trick to anything like this is going to be, from the information given, can you sketch a graph, right? Sketch a graph that looks like this, that has these features, and see what you can sort out. The domain we can 100% find for sure. The range might be a little sketchy, but let's see what we can do. So imagine that you went through the procedures that we talked about in class last time, and you found these things. The way you would start sketching the graph, we said last time, is by first drawing in the asymptotes. The asymptotes you think of as like a skeleton for the graph. So let me come out here to x equals 1, x equals 2, x equals 3, and draw in that vertical asymptote. There he is. That's the VA, x equals 3. The horizontal asymptote, y equals 0. Y equals 0 is the x-axis. So this is your HA, y equals 0. They told us at the point 1, -4, there's a hole. So let me come down here, -1, -2, -3, -4. So 1, -4, there's a hole here. And that's all they gave us. They want us to find the domain and the range. Now, what's implicit here, I suppose, is that there's nothing else special about this thing. Like, it doesn't have any x-intercepts. If it had x-intercepts, they would have told us that. And that's really the problem, is that they didn't give us that information. But if you try to draw the graph that sort of makes the most sense, you've got a vertical asymptote here. So you're either going to be going down, 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 or up, up, up. But there's no x-intercept over here. So it's got to be down, down, down. You're going to cross and do something like this over here. You're going to have the same sort of shape over here, right? All the graphs of the rational functions we see in this class have the same sort of hyperbola shape that we talked about. Okay, so here's a pretty reasonable sketch of a rational function that has these features. Vertical asymptote, x equals 3, boom. Horizontal asymptote, y equals 0, boom. Hole at 1, -4, there he is. So let's start with the domain. This is the same thing that we were doing at the very start of the semester, where you play that smooshing game. You're going to take this whole graph and go smoosh it down onto the x-axis. So this part of the graph over here would get smooshed onto this part of the x-axis, right? And just start shading bits of the x-axis that get hit when we play our smooshing game. This arrow indicates that this continues forever and ever and ever over here. So my domain is going to continue all the way out there. This part of the graph right here between my two fingers is going to get smooshed onto this part of the x-axis. But then this hole right here, remember the hole right here, that means there's no point on the graph there. So we're not going to hit this x value. But then this part of the graph down here, when I hydraulic press smoosh him up, he's going to hit everything over here. The vertical asymptote, remember vertical asymptotes, you find those at the same time you find the domain. There is no point on the graph whose x coordinate is 3. It's not possible because there's a vertical asymptote there. So we've got another number here that's not in our domain. X equals 3 is not in our domain. And then this guy, when I hydraulic press smoosh him down onto the x-axis, he's going to hit everything to the right over here. And of course, that continues on and on forever. So the blue shaded region on the x-axis is my domain. This x value here was 1. This x value here was 3. So my domain is all real numbers except for 1 and 3. And I'll give that to you in a few different ways in words. like this. Or in set builder notation, that would be the set of all numbers x such that x is not equal to 1 or 3. Or in interval notation, this would be negative infinity to negative 1, sorry, negative infinity to positive 1. Open, right, because we're not including 1. Union with 1 to 3, that's the pieces between here. Union with everything to the right of 3, that's 3 to infinity. That's our
So the worst part about that problem is the fact that when you get the right answer on that homework question, it actually wrote negative infinity to 3 union 3, 1 union 1 infinity.
Oh, yeah, that's a typo, isn't it? Okay, let me screenshot this. I'll send this off to the committee. This problem has several issues. Oh, I got you. We'll get this fixed. I'm sorry, guys. This is one of those things with a new online thing. They just made this last semester, so they're still working on it. All right. So yeah, this 3-1 interval, this is not correct, right? This should be 1 to 3. It should be 1 to 3. If it was 3 to 1, that's empty. That doesn't actually include anything. All right, let's take a look at the range. So if I play the same smooshing game onto the y-axis, what do we get? Use a different color for this. How about pencil? Pencil is something different. So this part of the graph here is going to smoosh onto all of this stuff. And this goes down and down and down forever. So this will go down and down and down forever. The hole here is a missing point on the graph, right? So that y value at that hole, that doesn't get hit. This chunk of the graph, when I could smoosh it in, is going to hit everything from -4 up to 0. But here we don't actually hit 0. Here we don't actually hit 0. So the horizontal asymptote does to the range the same thing that the vertical asymptote does to the domain. We don't actually cross over this. We don't actually cross over this. And then this part of the graph here, when I smoosh in onto the y-axis, he hits everything up here. So my range is going to be everything except -4 and 0. So in words, that's all real numbers. Except y equals -4 and y equals 0. And in the set builder notation, that would be the set of all y such that y is not equal to -4 or 0. And in interval notation, that would be negative infinity up to -4, union with -4 to 0, union with 0 to positive infinity. That's the shaded interval on the y-axis. Okay. So yeah, apologies for the errors in my open math here. This is one of the downsides of using an open source thing. It takes some time to find all the bugs and fix them, but I will get that fixed. I know that's not reassuring to you guys at this point. But maybe what would be reassuring is if something like this showed up on a test question. This is why I collect written work. If I can see in your written work that you followed the right steps, even if none of the answers that were available were actually correct, I would give you full credit for this. So if you gave me any of these expressions for the range or any of these expressions for the domain, regardless of how my open math marks your problem, I will give you full credit. So just make sure on the test you're showing your work, and no matter what sort of errors there are in MOM, everything will come out fine. The other one we wanted to see from his homework set was number 27. So here she is. Oh, this is actually, I think we did this the other day. So let's take another quick look at it. We want to find the domain and range y equals the square root of negative x plus 1 minus 6. A couple of viable approaches here. I think finding the domain, we can do this algebraically. And our domain rules. For the range, we need the graph. So we're going to have to graph this thing. Let me boot up Wabbit. We can review how to get a nice looking graph of this thing in the TI-84, TI-83. While we're waiting for Wabbit to boot, we can cook up the domain. So what sort of domain red flags do we see here? Guys, remember the domain red flag discussion, right? Stuff that when you look at the expression should set off some alarms in your head. One of the two are present here. Our two domain red flags were variables downstairs in a fraction or variables under an even root. The red flag we see here is variables under a square root. And this means we need to make sure that the inside is greater than or equal to 0. So that means I'm going to set the inside of this radical, right? Because this is an even root, it's a square root. We're going to set the inside, which is negative x plus 1 greater than or equal to 0. And the negative is just attached to the x. I want to point that out. That's different than having negative parentheses x plus 1. There are no parentheses around the x plus 1 here. So this negative is just attached to the x. And there's a couple ways you can solve this inequality. I think what most people would do is subtract the 1, which is fine. That'll give you negative x is greater than or equal to negative 1. And then you can divide both sides by negative 1 to get rid of this negative. So that will give you x is less than or equal to positive 1. Remembering that when you multiply or divide through an inequality by a negative number, the sense of the inequality flips over, right? So we go from greater than or equal to here to less than or equal to here because I'm dividing by the negative 1. So that's my domain. It's my domain as an inequality. If I want to write this in interval notation.
What happened to the 6?
So we're looking for the domain. And when it comes to the domain, all you have to worry about are these red flags. The 6 doesn't play any role in the domain. So the rule is if you have variables downstairs in a fraction, you have to make sure that that downstairs is not 0. Or if you have variables under an even root, then you have to make sure that the inside of that root is greater than or equal to 0. So in other words, this 6 doesn't have anything to do with the domain red flag, variables under an even root. Does that make sense?
Yes.
All right, cool. Yeah, so in other words, another way to think about this is how do you piss off this function, right? I know it sounds silly, but functions and algebra expressions, they have personalities. The only way to make this expression angry, right? Well, what are we doing here? We're going to multiply something by -1. We're going to add 1 to that. Then we're going to take the square root. Then we're going to subtract 6. The only way to make this thing angry is if you make the thing under the square root negative. There's no other step in that procedure, sequence of steps, where you could run into trouble, because you can subtract 6 from anything, but you can't take the square root of anything. There are some things we cannot take the square root of, namely negative numbers. So we need to make sure that the inside is not negative, it's greater than or equal to 0, and that just leads to this. So in interval notation, this is parentheses, -infinity up to 1 bracket. We have a bracket here because this is less than or equal to.
So if there's like a negative in front of the square root, it has nothing to do with the range then.
Nothing to do with the domain, but it
I mean,
will
the
affect
domain.
range. Yeah, that's true.
That's what I
Anything
meant.
going on outside the square root, if it's not inside the square root, it cannot affect the domain.
Okay. Could you show us how it would affect the range though?
Sure, let's do 2 versions of this. So we've already got our domain. I'll go ahead and finish solving this version, and then we'll do another version where there's a negative in front of the root, okay? So Wabbit should be awake. Let's see what we can get out of our graphing calculator, because to get the range, we really do need the graph. There are some tricks to this sort of thing that involve like shifting, flipping, stuff like that, the original square root graph, but we'll learn those in pre-calculus. Those are a little bit beyond us in this class. So I'm going to go ahead and type this function into the graphing calculator by hitting y equals, and then I'm going to type a square root, and then this button for the negative x plus 1. Before I type the -6, I need to make sure I get out of the square root. So I'm going to hit the right arrow button to get over to the right and out of the square root. Then I'll type -6. And I can hit graph. And okay, I can kind of see what's going on there, but look at all this space. Like, this is not the best possible picture. We did work from this last time, but let me play with my window settings a little bit. So the negative x values, those are good, but I had very little going on in terms of positive x values. Let me just shrink this down to like 3. And then y values, most of that graph was down there in the negative y values, but there wasn't much going on above the x-axis. Why is this not working? Maybe simplify that up and close those 2 things. Yeah, okay. Let me change that y max to like 5. And then we'll be a little bit more focused in on the area we're interested in. Okay. So here's our graph. This is looking a little more helpful. If I want to sketch that guy by hand, remember what we said about the graphs of these root functions. They all have the same basic shape, right? They either have that like S curve shape, or they have like the regular square root shape. This is that same thing, but it's been moved around a little bit. So if I hit my trace button, I can kind of walk over here and try to see what this point is. It's like it's 1, -6. If you pull up your table, you can see even better. Yeah, here's 1, -6. Down here, 1, 2, 3, 4, 5, 6. Here's that point, 1, -6. And then we can go back to the graph and kind of try to see, okay, it's got that like half of a sideways parabola shape, but it's just opening to the right instead of to the left. We can look at the table again to get a few more points, make sure we're really comfy with what we've got. 0, -5 is on the graph. So we're up here. Come to another nice point. -3, -4 is on the graph. 3, 4, something like this. So the shape, let me, yeah, I don't particularly like the way this is going to come out because of the scale. But it's about like this. Really what's going on is that you've got a shape like this. Right? It's stretched out to a point that it's kind of hard to see. But it's the same as that regular square root shape. It's half of a sideways parabola. This is kind of what it looks like at our scale. But This is really the basic shape we're dealing with. So the domain we already have, the range we need. If I'm going to squish this graph down onto the y-axis, the range is definitely, the smallest value on that range is -6, right? We never go below this. And there is a point on the graph whose y value is -6. And the question is, does this graph go up and up forever? Like, will it eventually be up here? Or does it stay down here this whole time? And the answer is, like all root functions, these go up and up forever. So our range is going to go up to infinity. And it might be a little bit hard to see that right away. If you're wanting to verify, just pull up your table. And we did this the other day. If you keep scrolling deeper and deeper into the -x values, you will find a place where this pokes through the x-axis, right? At -35, this thing becomes positive. And if you keep scrolling and scrolling and scrolling, you'll see that those y values, they do go up and up and up and up. They go up quite slowly. But this range does indeed continue past 4, past 5, eventually past 6. So this range will go up and up forever. Because we've asked about this before, I think it might be wise to take a quick look at a more friendly utility. So the TI graphing calculators, they're powerful tools for their time, but times have moved on. Here's our graph, all right, drawn in a much better utility. What you see is that same graph shape I was describing, right? Half of a sideways parabola. It really does look like this. It's just been shifted down and flipped over horizontally. And if we scroll our way out here, it really does just keep going up and up and up. There is no end to how tall that thing will get. It just takes its time getting there. If we really want to see it, we can change the scales. Let's say -1000 to say 2. Step size 10. Y scale something. So you can get a better feel for what's going on here by playing around with the scales a little bit more. And this guy really does just go up and up and up. Slowly, mind you, but he does go up forever. So our range, definitely starting at -6 down here, this is the lowest point on the graph. And this curve, although it might appear to flatten out, does go up and up and up forever. So this is our domain. And this is our range. Questions on this one? Okay. We wanted to talk a little bit about that 3-case rule for horizontal asymptotes. So let me first just remind you what the rule is, and then we'll look at an example of each. The 3 rules, so let me say R of x is a rational function, P of x over Q of x. Where P and Q are both polynomials, so they each have a degree. If the degree of the top, that is the degree of P of x, I'll just say degree of top, is strictly less than the degree of the bottom, like the top has maybe x's but no x squareds, and the bottom has like x squareds or x cubes or something like that, then the horizontal asymptote is the line y equals 0. If the degree of the top is strictly bigger than the degree of the bottom, then there is no horizontal asymptote. And the fun case is if the degree of the top is equal to the degree of the bottom, then there will be a horizontal asymptote. The horizontal asymptote is the line y equals, and then the way we say this is the ratio of lead coefficients. So think about what your rational function is. It's some polynomial divided by another polynomial. Every polynomial in the universe has certainly two things, right? A degree and a lead coefficient. Those are the things that we needed to sort out the end behavior for polynomials. So it makes sense that we would need them to sort out horizontal asymptotes, because horizontal asymptotes are really the end behavior for a rational function. What this third piece of the rule is saying is that if the degrees of the top and bottom match, like the top and bottom are both quadratics or both linear, then your horizontal asymptote is going to be the line y equals the lead coefficient of the top divided by the lead coefficient of the bottom. So I'll do an example for each of these. Let's say these three. So I have here three rational functions. Each one will require a different part of the three-case rule, which is there above. Looking at this first guy, what is the degree of the top?
Two.
Good. The top is degree 2. And the bottom, what's the degree there?
1.
1. Very good. So which one of those three cases are we in?
No horizontal asymptote.
Good. So since the degree of the top is bigger than the degree of the bottom, R of x has no horizontal asymptote. Oh. What about the next fellow? What's the degree of the top? The degree of the bottom.
Top is 3.
Good, the top is degree 3. And the bottom?
2.
So it's the same situation, right? No HA, because the degree of the top is bigger than the degree of the bottom. What about this guy? the degree of the top here is,
They're both 2.
yeah, they're both 2. So this is degree 2, this is degree 2. So which case am I in?
Where they're equal.
Yeah. So since the degree of the top is the same as the degree of the bottom, the horizontal asymptote here will be the ratio of lead coefficients. So the HA is the line y equals, I take the lead coefficient of the top and I divide by the lead coefficient of the bottom. 5/3 would be our horizontal asymptote there. I did miss one of those cases, so we can do one more. Let's add one extra guy in here. This is actually a neat function. I'll call it S of X. If you go on to take a calculus class, this function you will learn to love. It's called a serpentine. What's the degree of the top here?
1.
Yeah, this is degree 1, right? Because the largest power of X that shows up anywhere in the numerator is 1. And downstairs, that's degree 2. That's a quadratic. So because the degree of the top is strictly less than the degree of the bottom, the HA is the line y equals 0. This might sound a little bit silly, but when you're thinking about end behavior, when you're thinking about horizontal asymptotes, which is kind of what the function does for really, really big values of X, the basic idea underlying this rule is that you can kind of pay attention just to the lead terms. So here, the lead term upstairs is 6x squared. The lead term downstairs is 2x. So for very, very large values of X, this function behaves like 6x squared over 2x, which is 3x, which does not get closer and closer to any particular line. You know what the line y equals 3x looks like. Let me graph this for you in Desmos really quick. Actually, let me reset the graph. Six x squared plus 3 divided by 2x minus 1. All right, so you see no horizontal asymptote. The graph is not settling down on some line. But if I graph just 6x squared divided by 2x, isn't that neat? You see how the red graph is getting closer and closer to the blue graph? It's because for very large values of X, the red function is basically just doing whatever the lead term of the top says over the lead term of the bottom. That's how this rule works. If I replace this by any of our other examples here, like g of x was 5x squared minus 3x plus 2 divided by 3x squared plus 6x minus 1. And I just take the ratio of lead terms here. This is 5x squared divided by 3x squared. You see, the red graph is quite complicated, but for very, very large values of X, as you get further and further from the origin, it behaves just like the ratio of lead terms. And here the X squareds would cancel and you just get 5/3. That's why you have a nice horizontal line. Pretty cool stuff, right? So when you're looking for horizontal asymptotes, basically just ignore anything lower than the dominant term, right? Whatever the highest order term is, top and bottom, pretend like everything else is invisible. That will tell you your horizontal asymptote. And so the only case where you actually get a horizontal asymptote that is a non-zero number is if the degrees are the same, because then those x's would cancel, you get 5/3. Here, if we were to look at just x over x squared, that's 1 over x. So let's look lastly at if I just look at the ratio of lead terms. Turn off the blue really quick. So here, this is why we call this thing a serpentine. Pretty cool looking. And then if you look just at these guys, you'll see that the red and the blue get very, very close to each other as you go further and further out. And if you were to ask, what does 1 over x do as x gets bigger and bigger, that goes to 0. So the red is going to scooch in on 0 as you get further and further out. If you're seeing this stuff for the first time, I strongly recommend just thinking about it in terms of this rule, right? This rule is it will work for you 100% of the time. It will never leave you high and dry. You get 100% on every question that has anything to do with this stuff if you remember this rule. If you want to understand a little bit more deeply, though, think about what I was saying, just looking only at the highest order terms. Okay, so that's a nice revisit of horizontal asymptotes. We wanted to look at homework 12, question number 34 next. Let's go to that. So determine the domain, horizontal intercept, vertical intercept for each of the following functions. Write the domain in interval notation. Write intercepts as ordered pairs. If there is no intercept, write DNE. Does not exist. So horizontal intercept means x-intercept. Vertical intercept means y-intercept. So we want to find the x-int, y-int, and domain for each. We have f of x equals square root of x minus 8. F of x equals square root of 5x plus 10. G of x equals square root of negative 4x plus 36. And f of x equals the square root of 7x. Okay, let's start with the domain for each. All of these have variables under a square root. So the domain rule is the same for each. You're going to take the stuff under the square root and set it greater than or equal to 0. So to find my domain here, I just set x minus 8 greater than or equal to 0. I add 8 to both sides. That gives me x is greater than or equal to 8. And in interval notation, that is bracket 8 to infinity. All right, all the x values that are bigger than or equal to 8. I'm going to go through and find the domains for each of these using that same rule. Here I'll set 5x plus 10 greater than or equal to 0, because that's the stuff under the square root. I just need to make sure that that stuff isn't negative. To solve this, I can subtract 10 from both sides, and I get 5x is greater than or equal to negative 10. And next I'm going to divide both sides by 5. Is the inequality going to flip over when I do that?
No.
Good, because I'm not dividing by a negative number. The thing I'm dividing by on both sides is positive. It doesn't matter that this is negative. As long as the thing you're dividing by is positive, nothing happens to the inequality. So my domain here is all x's which are greater than or equal to negative 2. That's the interval negative 2 to infinity with the bracket on the negative 2. Same business down here with g. I'll set negative 4x plus 36 greater than or equal to 0. We can subtract 36 from both sides, giving negative 4x is greater than or equal to negative 36. This time, when I divide both sides by -4, the inequality will flip because I'm dividing by a negative number. So this is going to be x is less than or equal to, what is 36 divided by 4?
9.
Good. All right, and I'm dividing a negative by a negative, so it'll be positive. I'm dividing by a negative number, so the inequality will flip. So we get x is less than or equal to 9, which in interval notation is negative infinity up to and including 9. Lastly here, this guy, we just need to set 7x greater than or equal to 0. Same rule for each of these, right? Just setting the inside greater than or equal to 0. If you divide both sides by 7, you get x is greater than or equal to 0 divided by 7. What is 0 divided by 7?
0.
Still 0. Yep. If I've got $0 and I split it up evenly among my 7 friends, they each get jack shit. Okay, so that's the domain for each. Any questions on the domain? So the domain rule.
So just making sure it's always going to start as it's less than 0.
So the domain rule is if you have variables under a square root, then you need to set the inside greater than or equal to 0. So I need to make sure that whatever's under the square root is greater than or equal to 0, not less than. But yeah, same thing each time, always an inequality, always the inside greater than or equal to 0. What about, let's do y-intercepts next, all right? The vertical intercept. How do you find y-intercepts?
Plug in 0 for x.
Yeah, so to find the y-intercept, we always just plug in 0 for x. I'll start down here at the bottom. So y-intercept is always going to come from plugging 0 for x. That means we're looking at f of 0. So it would be the square root of 7 times 0. 7 times 0 is 0, so that's the square root of 0. The square root of 0 is 0. And we want this as an ordered pair. So the ordered pair, where x is 0 and y is 0, is the ordered pair 0, 0. That is your y-intercept. Oh, I didn't put this last domain in interval notation, did I? This would be 0 to infinity. Okay. The y-intercept for G, again, we're always just going to plug x equals 0. So that's going to come as G of 0, which is the square root of -4 times 0 plus 36. -4 times 0 is 0, so that's just the square root of 36. And the square root of 36 is 6. So the y-intercept here is 0, 6. This next guy, if I want the y-intercept, again, just going to plug in 0 for x. So it means I'm looking at f of 0, which would be the square root of 5 times 0 plus 10. 5 times 0 is 0, so this is just the square root of 10. And that's not an especially nice number. We just leave it as the square root of 10. You can plug it into your calculator and that will give you a decimal approximation, but the square root of 10 is an irrational number. So just leave it as the square root of 10. The first guy up here will not have a y-intercept. If you try to plug in 0, right, you can notice from the domain that 0 is not in this domain. This is just the numbers bigger than or equal to 8. You can try. If you plug in 0 for x, f of 0 is the square root of 0 minus 8, which is the square root of negative 8, which is not a real number, right? This is a non-real complex number, an imaginary number. So there is no y-intercept. Just like with your quadratics, when you're looking for x-intercepts, if the quadratic formula gave you imaginary numbers that told you that the graph had no x-intercepts, well, here, if you're looking for y-intercepts and you get an imaginary number, the square root of negative 8 would be I times 2 root 2, is not a real number. So there is no y-intercept on this graph. Any questions on the domain or y-intercepts for these functions? Okay. The x-intercepts for these are the ones that require sort of the most work. So I'm going to save these for last. The x-intercepts will have an equation to solve for each of these. We need to solve the equation f of x equals 0, i.e. you're going to set the function, the whole function, equal to 0. So if we take that first guy, f of x equals the square root of x minus 8, and we set that equal to 0, this will give us the square root of x minus 8 equals 0. If you square both sides, you get x minus 8 equals 0. And if you add 8 to both sides, you get x equals 8. So the x-intercept is the ordered pair 8, 0. For the next fellow, f of x is the square root of 5x plus 10, and you set that equal to 0, you have the square root of 5x plus 10 equals 0. Again, like squaring both sides, like we did here, squaring both sides. On the left-hand side, the square root goes away. On the right-hand side, 0 squared is 0, so you get 5x plus 10 equals 0. Subtract 10 from both sides, you get 5x equals 10. Divide both sides by 5, you get x equals 2. So the x-intercept is the point 2, 0. Okay. The other two go exactly the same way, so I don't think it's necessarily worth spending more class time grinding these out. You just set the whole thing equal to 0 to find the x-intercept. And because each of these functions is like the square root of some stuff, Your first step in solving that will be to square both sides. And what you end up with is just the stuff inside equals 0. Anything we want to look at more closely here? Oh. So it's number 34. The next one is, how do you enter roots higher than 3 on the older TI-84? I might need a little bit of clarification on that. So if we want to enter, what do we mean by enter a root higher, like a cube root or 4th root, 5th root, 6th root? That sort of thing?
A cube root, I'm pretty sure it's on a question on homework 12. It's like the same table that we had there, but they just have cube roots.
So, talking about stuff like
Yeah,
that.
31, yeah.
Okay. So, say for example, I wanted to find the x and y intercepts for g of x equals this guy. We'll talk about this for a minute. I'll modify this a little bit. Find the, no, let's just say y-intercept. G of x equals the 4th root of negative 4x plus 6. And f of x equals the, let's say, 5th root of 3x plus 32. So one thing at a time. You can always work these out by hand and leave your answer in terms of the root. So we know that the y-intercepts come from plugging x equals 0. And that's true for all functions, right? Not just rational functions, not just radical functions, not just polynomial functions. It's true for all functions. If you're looking for the y-intercept, you're going to plug in 0 for x. G of 0 here would be the 4th root of negative 4 times 0 plus 6, which is the 4th root of 6. That's negative 4 times 0 is 0. You could leave your answer like this. That's okay. If you want to write this as a decimal, if you want to plug this into your calculator, two paths. One option. There is an nth root feature on all TI-8384s. It's hidden, but it does exist. So let me get out of here. If you hit math and you scroll down here where you see the x root, you can bring that up. Oh, I'm just trying to use my previous answer for the x root. Okay. X root. That should ask me for the root I want. Okay. So if I type, that's what it's going to do, type 4 and then math and then x root. That'll give me the 4th root of whatever I want, 4th root of 6. Blank. That's one option. About 1.565. Another option is to use one of the rules for exponents that we talked about. The nth root of a number is the same as that number raised to the 1 over nth power. So the 4th root of 6 is 6 to the 1/4. Check this out. If I go 6 raised to the, and then you might want to put your exponent in parentheses if you're on an 83. Just for good discipline, I will do that. Blam, same thing. So the rule there, remember, we talked about this when we introduced power functions, is that the nth root of a is the same as a to the 1 over n. So you can always get the nth root of a number by typing in the 1 over n power of that number. That is an option. Or you can use the nth root function in the calculator. And again, the way we did that is by typing 4, then math, then we go down to the x root button, and then type the 6. We can do the same over here. So again, we want y-intercepts. So we're going to plug x equals 0. And we're looking at f of 0, which would be the fifth root of 3 times 0 plus 32. I chose this one to come out nice. 3 times 0 is 0. The fifth root of 0 plus 32 is the fifth root of 32. I could plug this into the calculator, but I also know that 32 is 2 raised to the fifth power, right? 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, 2 to the 5 is 32. But we can see how to enter it here. I would probably just type 2 raised to the 1/5. I think that's a little easier than using that nth root function. It'll give me this. Or I could type the 5 for the fifth root, then hit math, then scroll down to the xth root function, and then type 32. Oh, what did I do? I typed 2 to the 1/5 there before. That's not what I want. Yeah. So the fifth root of 32 is 2. Or if you type it the other way, 32 raised to the 1/5 power is 2. So either way, you can say this is 2, or you can say this is the same as 32 to the 1/5 power, which is also 2. But in general, this is your rule. If you need to check something in the calculator, or for whatever reason you need a decimal for one of these things, the nth root is the same as the 1/nth power, just like the square root is the 1/2 power. Cube root is 1/3 power. Fourth root is 1/4 power, and so on. We do have a little bit of time left. Is there anything else you guys would like to look at in our remaining 7 minutes? Any other homework or quiz questions?
Question 28 for homework 12.
Sure. So they say the time it takes for a pendulum to swing back and forth can be represented by the function s of x equals 2 pi times the square root of x over 32. The output, s of x, is the time in seconds, and x is the length of the pendulum in feet. They ask, how many seconds will it take for a 5-foot pendulum to swing back and forth one time? S of x is 2 pi is the square root of x over 32 is the time for a pendulum to swing where s of x equals time in seconds and x is the length in feet. So if we have a 5-foot pendulum, we want to know how long will it take for a 5-foot pendulum to swing. So what this function takes as its input is the length of the pendulum, and what it spits out as its output is the time for the thing to swing. So in part A here, what we're asking for is s of 5. And that would be 2 pi times the square root of 5 over 32, which is 2 pi times, and there's no nice way to simplify this, right? 5 and 32 don't have any common factors. So I would come into my calculator and just ask for the square root of the ratio of 5/32. I get about 0.395. I guess it's not approximately. And then if I multiply that by 2 pi, you type a pi by hitting second and then this caret. You see the little blue pi here? You get 2.484 if we round up the third decimal place. So it'll take about 2.5 seconds, right? About 2.5 seconds for a 5-foot pendulum to swing back and forth. We can see if they agree with us. Yeah, rounded to 1 decimal place, 2.5. Cheers. In part B, they say it takes 6 seconds for the pendulum to swing back and forth 1 time. What's the length? So part B, if a pendulum takes 6 seconds to swing, how long is it? So here, rather than giving us a length and asking for the time, right, rather than giving us an x value and asking for the output, they gave us a time, which is an output, and they asked us for the length. That means we need to set s of x equal to 6 and calculate x. So we need to solve the equation s of x equals 6. And if I take s of x and I plug in the function there, s of x is 2 pi times the square root of x over 32. Set that equal to 6. We can then try to solve. My first step in solving an equation like this is going to be to divide by 2 pi. My goal is to get x alone. So when I divide both sides by 2 pi, I get the square root of x over 32 equals 6 divided by 2 pi. I think it's wise to go ahead and cancel the 6 and the 2 at this stage, just to clean up your arithmetic down the road. So 6 divided by 2 pi is the same as 3 divided by pi, because 6 is 2 times 3. You can cancel the 2. Next, if I square both sides, I'll get x over 32 equals 3 over pi squared. And I square both sides to get rid of the square root. Like in the previous step, it's smart to clean up the result over here before trying to go further. So I'll have x over 32 equals, well, 3 squared is 9. Pi squared is just pi squared. Leave it as pi squared. And then my very last step will be to multiply both sides by 32. So I get x equals 9 over pi squared all times 32. And they wanted us to round, so we'll go ahead and put this into our calculator. You just need to be careful with your order of operations. This is 9 divided by, again, your pi is right here, so that's second, and then that caret button. And that pi is being squared. So 9 over pi squared, plug this in, make sure it makes sense, right? Pi is about 3-ish squared, should be about 9. 9 over something close to 9 should be close to 1. 0.9, yeah, that's close to 1. Make sure your answer makes sense. Then multiply this by 32. You get 29.1805. It's 29. If we round that, it's barely 29.181. They wanted round to 1 decimal place, right? So this would be more 29.2 if we round to 1 decimal place. So it'd be about 29.2 feet. Cool, right? Okay, we will go ahead and end it here for the day, guys. If there's anything else you want to see, anything else you're worried about, anything like that, please come to office hours. I've got an office hour starting at 11, or send me a Canvas message. Just reach out to me in one way or another and let me know how you're doing. If there's something that you need coming into this test, let me know and I will help provide it for you. On that same note, if you know, as the test approaches, right, say next Monday, you've been studying all weekend long and you're trying, but next Monday arrives and you're like, I'm totally fucked. There's just no way for this to go well. Or you find yourself starting to do that thing where you're like, where can I hide a phone? Where can I hide a cheat sheet? Anything like that. Instead of continuing down that path, please reach out to me and let me know. I can move you into the makeup group, which will give you a few extra days to study. Of course, it's preferred to take the test on the test day because that avoids falling behind, but I'd much rather give you a little bit of extra time to study than have to deal with cheating. So please don't back yourself into a corner. If you feel yourself there after trying to prepare for the test, let me know and I will work with you. But otherwise, that's it. Please study hard for this test. Go over the test review quiz. I apologize for that having been locked. I don't know why it was locked again. It's a trial run of MOM, so there are some bugs that we're working out, but it is unlocked now. Get in there, work that review quiz. If you have problems, questions you want to talk about, bring them to office hours. Send me a Canvas message. Take a picture of your work and share it with me, and that way we can work together to make sure you're ready for the test. All right. That's it from me, guys. Take care.